All right. So, as a recap, I said a few things before I started this recording. So, for people watching this in the future, um, uh, antiderivatives, this section right here, 3.7. Where are you? This section, 3.7, is not going to be on exam 3. 3.7 will be on the final exam, but it's not going to be on exam 3. It is part of the homework for this week, but it will not be on the exam. The exam review that's posted will not have this material on it. Just because the topic is pretty drastically different than the rest of the surrounding topics for exam 3, I want to make it a little bit more streamlined, and I'm going to put this on the final, but not on this one, on exam 3, so that it flows a little better. All right. Okay. And exam 3 will be available on Monday of next week. The tentative due date that we have posted on the calendar is Friday of next week, but I think I'm going to give it through Sunday of next week. I've kind of made that extension for all the exams at this point, so I think I'm just going to make that extension again, and that way you have Monday through Sunday to work on it. All right, so let's go ahead and get started. We started talking about initial conditions, so we talked about antiderivatives, which are, once again, the opposite of a derivative. So if we go back, we're used to kind of going in one direction where we have a function and then we take its derivative, but the antiderivative is going the opposite direction. We have a derivative, we want to find the original function again. Now, the interesting thing with derivatives, there's one derivative. You have a function, you take its derivative, that's the derivative, you're done. But with antiderivatives, there are infinitely many functions that can give you the same derivative. So when you go in the backwards direction, you have this constant that's not accounted for. And in a lot of cases, if you're talking about general antiderivatives, you just have this constant added on at the end. But if you're given more information, like in these initial condition cases, you're able to use that additional information to solve for the constant. And there is one of those problems on the homework that is posted for this week. All right, give me just a second. Just need to grab some water real quick. Hold on just one sec. All right. Got myself some water. So let's try this one. We had done a few, but we have y double prime is equal to sine x, and y of 0 is equal to 1, and y of pi is equal to 3. In the previous example, we did something similar. We had y double prime equal to sine. But notice in this previous example that we did, we had y prime of 0 is equal to 1 and y of 0 is equal to 6. So we had information about y prime and about y. The difference between these two is that in this example down here, we have information about y and y only. So when we take the first antiderivative, we're not going to have enough information to solve for this constant. So let's see how that works out for us. So we're going to start with the antiderivative of y double prime, which is y prime. So we're going back a derivative. With sine, sine's antiderivative is negative cosine. And then you're adding that constant on. Once again, to repeat myself, we don't have any information about y prime, so we cannot solve for this constant down here. So we're just going to have to go the next step of finding the next antiderivative, which will give us y. So the antiderivative of y prime is y. So cosine, so we have this negative out here. This is the same negative. Now remember, cosine's derivative is negative sine, but cosine, his antiderivative, is positive sine. So this negative is coming straight down, and then cosine's antiderivative is sine, just like we did before. C right here is a constant. So when we integrate a constant, not integrate, we haven't used that word yet. When we find the antiderivative of a constant, we're just adding an x onto it. So That was what happened here with the 2. 2 became 2x. Now, we've already used c as a constant here, and we're talking about two different constants. So we have c, we're going to use a new constant and call it d, because we've already used the constant c once. At this point, we now have an equation where we have two constants we need to solve for, and we have 2 bits of information here. Now, these 2 bits of information are coincidentally going to be the right bits of information that allow us to solve for both pieces easily. So this will make it pretty easy to solve for it. So we'll start with y of 0. So we have y of 0 is equal to 1. So 1 is equal to negative sign of 0 plus c times 0 plus d. Sine of 0 is 0. C times 0 is 0. So you're going to get 1 is equal to d. That can be plugged right back in for d up here. So you now have y equals negative sine x plus cx plus 1. The next bit of information we have is this, and let me underline this right here. The next bit of information we have is y of pi is equal to 3. Right? So 3 is equal to negative, and we're using this function right down here. 3 is equal to negative sine of pi plus cx plus 1. Right? Negative sine of pi is going to be 0. Oops. What did we forget here? Plugging in for x, right? So you're not going to have an x there. You're going to have a pi. There we go. Much better. Negative sine of pi is 0. Pi times c is going to be pi c, or you could call it c pi. I like pi c. I like to have that variable at the end there. Plus 1. Subtracting 1 on both sides, you get 2 equals pi c. Solving for c, you're going to get 2 over pi. So now you have all the information necessary because you can plug this 2 over pi in, and bam, you got yourself y equals negative sine x plus 2 over pi x plus 1. And can I answer any questions about that initial condition problem? I'm going to find some practice problems to do real quick on it, but are there any questions on that one? All right, so let's find one for us to practice. So I'm not seeing any questions come in. I'm just going to go based on the, let's see, the exercises I posted. So I'm going to give you 2 to try out. So in both of these, you're going to be finding f. So let's see. The first I'm going to give you f prime of x is equal to 5x to the 4th minus 3x squared plus 4. And f of negative 1 is equal to 2. And then I'm going to give you one more. F double prime of x is equal to 8x cubed plus 5, and f of 1 is equal to 0, and f prime of 1 is equal to 8. So I want you to do both of these. For both of these problems, you're finding f, right? This is a first derivative, this is a second derivative, so the process is going to be a little longer for part B. I'm going to give you, let's say 5 minutes to work through these ones. I think that should be enough time. So 5 minutes, work through these ones real quick, and then we will talk about those answers. All right, so my timer just went off. So how are we feeling about these? Before we go through the answers, how are we feeling about these two problems right here? Pretty good, I think. I like that answer. Good, pretty good. I'll take those. I'll take those. All right, let's do this. Let's see if I can separate these a little bit. Bam. All right. So starting with this first guy. So we're going to f of x now. So we are taking the antiderivative. So this 5 will stay out front. And then remember, there's a mental trick here. So I'm going to talk about the mental trick after I do it the long way. But you're taking the exponent, you're adding 1 to the exponent. So that's 5. And it's 1 over 5 x to the 5 minus 3. Adding 1 to the exponent, that's 3. So 1 over 3 x to the 3. With constants, you're just adding on an x. So 4x plus c. Simplifying here, those 5's cancel. So this will be just x to the 5th minus these 3's cancel. So x cubed plus 4x plus c. This is f of x. So the mental trick that I do, that the point you want to get to, because you don't want to be writing down this step every time, you do want to get to the point where you're getting really quick at these. The mental trick that I do is I'm adding 1 to the exponent and then dividing the front number by whatever number I get. So in my head, when I'm doing these, 4 plus 1 is 5. 5 divided by 5 is 1. So I get x to the 5th. Add 1 to the exponent, that's a 3. 3 divided by 3, that's going to be a 1. So that's how you're getting here. Now we have that f of negative 1 is equal to 2. So we have 2 equals negative 1 to the 5th minus negative 1 cubed plus 4 times negative 1 plus c. So we have negative 1 plus 1, those canceled out. Minus 4 is plus c. So we get c equal to 6. And then our final answer, because we don't just want the constant, you want to come back and plug it right back in here. You get x to the 5th minus x cubed plus 4x plus 6. How was that one? Did that one come out okay? Yay! Good. Excellent. Excellent. That's what I like to see. Great, great. Okay, cool. All right. Now with this guy, with part B, our first antiderivative is going to go to f prime. And if I'm using my mental trick here, see how this works? 3 plus 1 is 4. 8 divided by 4 is going to be 2. So we have 2 x to the 4th, and then the constant gets an x plus c. Now here's where you have to be careful, because I was kind of doing this on a scratch piece of paper. And, you know, my brain's a little fuzzy at times, but I went for this first piece of information because my brain wasn't thinking about the fact that this could be misordered. So the order in which you use this information might not be given to you correctly. So here you have this information, but you're not using this information on this equation. You're using the f prime one. So it's really important, because if my brain can make that mistake, anyone's brain can make that mistake, that you're looking to make sure that the information matches up. When I go talk about f prime, I want to make sure I'm using the information for f prime. So we know that f prime of 1 is equal to 8. So 8 is equal to 2 times 1 to the 4th plus 5 times 1 plus c. 8 is equal to 7 plus c. We get c equal to 1. So rewriting f prime, we have 2x to the fourth plus 5x plus 1. Now we're finding the next antiderivative, that's f of x. So adding 1 to the exponent, we get 5. So this is 2 over 5 x to the fifth plus, add 1 to the exponent, that's a 2. So 5 over 2 x squared plus x plus c. Now we'll use the next bit of information, that f of 1 is equal to 0. So 0 is equal to 2 fifths, 1 to the fifth, plus 5 halves times 1 squared, plus 1, plus c. Right, so we have, let's see, 14 tenths, yeah? Plus 1. Let my brain do something real quick. All right, so 0 equals 3.9 plus c. Did we get c equal to negative 3.9? Or if you're doing it as a fraction, this would be negative 39 over 10 for that last value there. For a total of f of x equal to 2 fifths x to the fifth plus 5 halves x squared plus x minus 3.9. Is that the answer that we came to? Not seeing any chatting yet, so either I'm not catching a mistake or maybe there was some confusion. Okay, I see a yes. I see a yes. That was an answer we came to. Are there any questions on either of those examples? Oh, that's no problem. I actually, on my own scratch paper, had calculated it wrong. On my own scratch paper when I was doing this, my brain said that it said that 8 divided by 4 was 4 in my brain, which actually ended up ruining my calculations down here. But you know, sometimes the brain just does those things. But does that process make sense to everybody? Cool, excellent. Great, great. So if there's no questions, then the last thing to talk about for antiderivatives, and this whole idea of antiderivatives, this isn't going away. So while this isn't on exam 3, this antiderivative idea actually builds up that whole idea of, let's see. It builds up this whole idea when I talked about how the calculus is set up, like in a quarter system versus semester system, and we're going to talk about integrals. Antiderivatives are the basis for integrals. So what we're going to be talking about in Unit 4 is integrals. So this idea that we're talking about right now will not go away. It's just going to get stronger and stronger. So this is really just the basics we're talking about at this point. So don't worry if you're like, wow, I feel like I could use a lot more practice on it. You will get it as soon as we start talking about Unit 4. And I'm going to remember to constantly stop the recording and restart the recording just to make sure that all those segments aren't getting corrupted. Like, you get one 90-minute segment gets corrupted. I will never not put it into small segments again. All right. So finally, like I've talked about before, one of the big connections that calculus has to the real world is in physics. And we've talked about some stuff before. in particular, we've talked about how we have like a position function, right? We have s of t, and this was the position function. And then if we took the derivative of position, that gave us the velocity function. And that if we took the derivative of that, so if we took the derivative of velocity, that gave us an acceleration function. Now, it would only make sense that if we can go in that forward direction, if we can take those derivatives, that we could go in the backwards direction. And right, if we have information about acceleration, then we could probably find some information about velocity and position. And that's exactly what we're going to do. So once again, previously we're given information about the position, then we found velocity or acceleration. We're going to work in reverse. As an important note, if no other force is acting on a falling object, typo here, object, then the acceleration is only due to gravity, which is negative 32 feet per second squared, or negative 9.8 meters per second squared. Here's the thing. I'm not a physicist. I don't claim to know physics. All right. Clearly, everything we're talking about is oversimplified, and if you've taken some physics courses, you might even know more physics than I do. So everything we're talking about here is an oversimplified version of physics. So just kind of go with the flow with this. All right. Go with the flow. But in general, if no other force is acting on a falling object, then the only acceleration they're going to have is negative 32 feet per second squared, which is gravity. So in general, a lot of these problems, they're set up using one of these two numbers, depending on what your units are in. So let's talk about this. A balloon rising vertically at a velocity of 16 feet per second releases a sandbag. When the balloon is 64 feet above the ground. A, how many seconds after its release will the sandbag hit the ground? And B, what will be the velocity of the sandbag when it hits the ground? Round your answer to 2 decimal places. So starting with part A, how many seconds after its release will the sandbag hit the ground? So the important part here is sandbag hits the ground. And we have to think about what that means for us. So if we draw like a really rudimentary picture here, there's a balloon. I don't know what a sandbag looks like, but I'm going to draw this, right? And here's the ground. And we're dropping this. What the position function is going to mean for us in this case is probably something to do with the height above the ground, right? That's our position. So our position function here won't be talking about like horizontal distance. Our position function here is really talking about the height above the ground. Where, here we're up here at 64 feet when the bag is released. Down here, when we hit the ground, what would our position be? What's the position what would the position function give us if we're hitting the ground? What would S of t be in this case? If our position function represents the height above the ground, when you hit the ground, that value should be 0. There it is. Yeah, so the position function should be 0 when the sandbag hits the ground. So this is asking us to find the t value that makes position equal to 0. And I say t value because I mean time. So position equals 0 is the same thing as saying S of t equals 0. Now, the information we have here is that acceleration is equal to negative 32 feet per second squared. We are talking in feet here. So we know that acceleration is equal to negative 32. We need to get ourselves to the position function. If I look up here, acceleration is the same thing as s double prime. Knowing that connection there makes it so we can now work through the process backwards the way that we have before. So the antiderivative of s double prime is s prime, which is the velocity function. And just to kind of reiterate right up here, s prime of t is the velocity function. Just as a note. All right, so s prime of t, we're just going to add a variable. Now it's not an x, it's going to be a t. It's a t because our variable is t plus c. Okay, well, we're going to need to solve for that c, right, eventually, because if we keep on going, there's going to be a problem in that if we want to find where eventually s of t is equal to 0, we're going to need these constants solved for. So there has to be some more information given to us. So we go back up here and look. Is there any information given to us about s prime of t, which, once again, is velocity? Well, in the very first sentence here, it says it's rising vertically at a velocity of 16 feet per second. And at the moment where it releases the sandbag, that is its rising velocity. So we know that at time equals 0, that the velocity was 16. Let me write that a little bit. Does that make sense? Does that make sense that the velocity would be 16 when time is equal to 0? Because if we think about how we're defining time, time is going to start when we drop the balloon. Time starts, we start the clock when we drop the balloon. And at that moment, what we know is that the velocity was 16. So we know that v of 0 is equal to 16, and s prime of t is the same thing as v of t. So 16 is equal to negative 32 times 0 plus c, which means c is equal to 16. So let's not use purple, let's use green. Well, let's use purple. So v of t, which is the same thing as s prime of t, is equal to negative 32t plus 16. I don't like the way that that's positioned. Move it down a little bit. And it's kind of like we're going through this in stages. So we've dealt with the antiderivative of s double prime, and now we're going to go into finding s. So the antiderivative of s prime of t is going to be s of t. So we're going to find that antiderivative again. So using that mental math trick, add 1 to the exponent, you get a 2. Negative 32 divided by 2 is going to be negative 16. Adding on t onto the constant, plus c. Now we're looking for more information. Oftentimes these physics types problems, there's going to be some physics type problem on the final, right? There's going to be some physics problem. And often these physics problems, you just have to kind of go back and grab information. So then you look and say, Releases a sandbag when the balloon is 64 feet above the ground. Releases sandbag when the balloon is 64 feet above the ground. So when time is equal to 0, at the moment where we release the balloon, the position was 64 feet. When time was 0, the moment we released the balloon, not the balloon, the sandbag, the position was 64 feet above the ground. So S of 0 is equal to 64. 64 equals negative 16 times 0 squared plus 16 times 0 plus c. You're going to get c is equal to 64. Plug that right back in. And you're going to get S of t is equal to negative 16t squared plus 16t plus c, not plus c, plus 64. Now that feels really great, and you're like, I am done. I have found my answer. There's S of t. But wait, there's more. Because that's not what we wanted, right? In the end, what problem A asked for is, going back to what we wanted, need to find the t value that makes the position function equal to 0. So I'm kind of trying to put this into steps here. Now find t that makes S of t equal to 0. So 0 equals negative 16t squared plus 16t plus 64. I'm just going to tell you that this thing does not factor nicely. You can factor out a negative 16 if you'd like. That's totally fine. So you'd get t squared minus t minus 4. But this thing doesn't factor nicely. You will need to use the quadratic formula here. But if you factor out the negative 16, at least your numbers are nicer here. So using the quadratic formula, x is equal to negative b, so negative negative 1, positive 1, plus or minus square root. B squared is 1, negative 1 squared is 1, minus 4ac all over 2a. And if you plug those in your calculator, so this ends up being 1 plus or minus the square root of 17 over 2. If you plug those in your calculator, the plus and the minus one, you get 2.56 and also negative 1.56, as long as that calculation is right. But because I did that on my notes a while ago, let me just make sure. Yes. Yes. I'm getting two numbers here. Any ideas of what we want to do with those two numbers? Is there two answers? Can I say, so I don't think so, is what someone said. I'd agree. I don't think there should be two answers. What are these values representing? These t values. What do these t values represent? Time. They represent time, exactly. And time was 0 when we released the sandbag. So saying that we hit the sandbag hits the ground at negative 1.56 seconds, that doesn't quite feel right, because that would mean prior to releasing the sandbag hits the ground, which that doesn't sound right. That doesn't feel right. So we can't have negative time. You can't get time back. So the only answer we have here is this 2.56 answer. So t is equal to 2.56, and then remembering our units, seconds. And my internet on my computer just crashed. I'm not sure if it crashed on here, so and we're back. All right, so that was the answer to part A, which you might say that takes up a lot of room. How are we going to have room for part B? But part B actually doesn't take that long. So part B is, what will be the velocity of the sandbag when it hits the ground? Well, looking here, we hit the ground at 2.56 seconds. That was what we found in part A. We hit the ground at 2.56 seconds. And we have a velocity function right up here. Velocity function tells us what the velocity is at any given time, negative 32t plus 16. So all I have to do, what this is really asking me for, is the velocity at 2.56 seconds. So we just need to plug in 2.56 to this function, and you should get negative 65.92, and then our units will be feet per second. Now, while time can't be negative, I think maybe it's worth saying that your velocity can be negative, and it would make sense given the picture we have here that velocity would be negative, because we said that the velocity was positive when we were rising, right? The velocity was positive when we were rising. So the velocity being negative when we're falling would make sense in the context of the picture. It also makes sense in the context of what acceleration is. So if acceleration is negative and gravity is that acceleration, that means that the acceleration is talking about moving in that downward position. Can I answer any questions on this problem we just did right here? Any questions at all on antiderivatives that I can answer? All right. So then I did say, like I said, I think we're going to cut it a tiny bit short today, but I do want to talk about just kind of what's going to be on exam 3. We're on exam 3. So all of these sections that we talked about, so we didn't talk about differentials, so don't worry about differentials, and we didn't talk about the mean value theorem, so don't worry about the mean value theorem. But those, the 3.1 extrema on an interval, 3.3 derivatives and graphical interpretations, curve sketching, optimization, those are all going to be on exam 3, right? This antiderivative stuff that we just finished talking about, this will be on the final exam. So there is a bit of information. So all of Unit 4 happens after exam 3. So exam 1 covered Unit 1. Exam 2 covered Unit 2. Exam 3 covered most of Unit 3. And then the way the final exam works is the final exam is comprehensive. So about half of the material is going to be from Units 1, 2, and 3. And then the other half of the material, so it'll be more heavily weighted towards the Unit 4 material. So half of the material on the final exam is going to be from Unit 4. So there's no like test 4 and then a final exam, I think it's a little excessive to have you guys doing a test and then immediately do a final. So half of the final exam will be Unit 4 material, and then half of it's going to be from Units 1 through 3. So it is a comprehensive final, but more weighted towards the Unit 4 stuff. So just as an idea of of how that's all broken down. So you will see this stuff again just on the final exam. All of this stuff here is the stuff that you need to worry about for exam 3. Extrema on an interval, to kind of recap on that. Let's see. Going through all these. When you're doing extrema on an interval, that's where you're finding those critical values, right? So you take the derivative, set it equal to 0, find the critical values that are within the interval you're given, and then you plug them back into the original function. So you're finding with the extrema on an interval, typically you're finding the absolute extrema, and the absolute extrema you get from plugging back into the original function. So you find the critical values, and you plug the critical values along with both endpoints back into the original function. Okay. Then we talked about derivatives and graphical interpretations. So we talked about, what a mess this is, huh? We talked about what f prime means for the graph of f. So if f prime is positive, your original function is increasing. If f prime is negative, your original function is decreasing. If f prime is equal to 0, if it's equal to 0 at just a point, then you have one of these like flat areas. But if it's equal to 0 on an interval, that would just mean the function is constant on that interval. So we then talked about the first derivative test. I'm just kind of trying to give a review of those things that we've talked about. We talked about the first derivative test, and one of the problems on your homework that was due what day is today? Where are we? Wednesday. The homework that was due Monday, so not yesterday, but the day before yesterday, one of the questions asked you to do the first derivative test and asked you to do the second derivative test as well. So this first derivative test is where you're making a sign chart, right? The first derivative test has you making a sign chart. You take the first derivative, you find your critical values, your important values rather. So all the values, even if they're not critical values, even if they're not within the domain of the original function, you find all important values. And you're making a sign chart, and then you use that sign chart to find any potential local maxes or mins, and then you can find the increasing, decreasing, and all of that. But the first derivative test in general is finding the local maxes and mins, and you're finding the local maxes or mins based on how it changes from decreasing to increasing, or increasing to decreasing. The second derivative test the second derivative test, on the other hand, you find the critical values or the important values just like you do with the first derivative test. And you find those from the first derivative. Always are finding those important values from that first derivative. And then you take the second derivative and you plug in the critical values to find out the concavity there. Because if you know that if you know it's a critical value, then you know that that the derivative is 0 there in most cases, or undefined. So you know it's like going to be like maybe something like this or something like this. I mean, it could also be a situation where it's something like this. But if you know the concavity, so in this case right here, you're actually looking at like an inflection point because the concavity is changing there. But on these situations where it's a max or a min, if you know that it's 0, the derivative is 0, and then you plug in that x value to the second derivative to get its concavity, you can find if it's positive concavity or negative concavity. And if it's positive concavity, then you're going to have a minimum. And if it's negative concavity, then you're concave down, you're going to have a maximum. So the second derivative test doesn't involve a sign chart, whereas the first derivative test does. In most cases, you're welcome to do either. The problem with the second derivative test is the second derivative test can fail. So in a situation like this, you'd end up failing. But there's also situations where it actually is a max or a min, but the second derivative test fails. So if you get f double prime equal to 0, so if you plug in into your second derivative and you get 0, that means anything could happen. It could be a max, it could be a min, it could be nothing. That means you have to use the first derivative test. So the problem with the second derivative test is A, sometimes your second derivatives are messy, and B, the second derivative test does have the probability of failing, whereas and that's not in every situation, just there are situations where it fails, and the first derivative test will not fail you. So you could be putting a time investment into finding a second derivative and have that not work. There was some graph interpretation problems in section 3.3 that are important. On the exam review that you'll see that was posted, I think I have 4 different problems that involve reading a graph, and the graph is either the derivative or the second derivative. When we did the exam review on Friday, and I'll post about the exam review, say what time it's going to be and everything, and it will be recorded so that you can watch it later if you can't come on Friday. We'll talk about those problems more in detail, but I want you to think back to this problem when you're doing the exam review, to think about the kind of thinking we had to do to answer this problem. And I know there's a lot going on here. It's kind of hard looking at it here. But it gets interesting when you're given the graph of the derivative or the graph of the second derivative, and you're trying to answer information about the original function or the first derivative or the second derivative. The next part was curve sketching. Right? Reviewing curve sketching. Remembering that there's basically 4 different shapes that get made based on increasing, decreasing, concave up, concave down. And we talked about the important part of curve sketching being to decide which of these shapes you're going to make on any particular interval. To me, I think it's most important, if you know the concavity, then you can kind of look at the picture of the concavity, and then if you know the increasing, decreasing, you split that split that picture in half, and you can say, okay, this is the decreasing part of concave up, and this is the increasing part of concave up. Right? So when we were doing examples over here, we had information on different intervals, and the way that we sketch the graph, I make these really light lines. These light lines are not asymptotes. These are just places for my brain to recognize that we split up the graph, that something changes on the graph at that point. So I just like to make these really, really light lines that are just for my information when I'm curve sketching. The way that you break down this little chart down here, you go to the intervals. So the intervals where it tells you about f prime, f double prime, and sometimes you have to find these intervals. So some problems you're finding the intervals of increasing, decreasing, and then concave up, concave down, but you want just the interval part, and then you take all the x values that you have for any of these 4, and you break it up below the graph. So if there's a -5, you're going to put -5 here, draw a line. If there's a +5, you put 5. There's a -2, 0, and 2. You're going to break up this whole thing down here. And then you're using information that you're given to say whether it's increasing or decreasing, and whether it's concave up or concave down. Right? I do this before drawing a single thing on this graph. I do this little table down here. This little table is everything I need to do to make my graph successful. From there, now I have this information. I look at this picture. So before you've drawn any of this, right? When this part is non-existent, you're determining what this shape is right here by looking at this concavity and then saying, okay, in your head, you're splitting it in half. You're asking yourself, do I choose this left side or the right side? If it's the decreasing part, right, this is the decreasing part. So I'm choosing this shape right here, which is what I ended up drawing here. There's a bunch of ways to do curve sketching. If this way isn't the best way for you, there are many resources online that talk about curve sketching and different ways to do curve sketching. This is the way that I have found is most successful for me. It's the way I like to organize my work, but you're more than welcome to find other ways to organize your work too. But do make sure you are organizing your work, because the most important part of being successful at curve sketching is making sure your work is organized. I find that this does a good job because I know where it's going to break up into different shapes, right? And that shape is right down here for me to refer to. For the actual drawing of the graph, you want to plot any points you have first. Those typically include, but not always, they include asymptotes, horizontal or vertical, intercepts, maxes, mins, inflection points. On problems where you're finding the information, any maxes or mins, you should have the coordinate points of those to plot. Once you've plotted any points that you have, then you're just looking at, you want to make sure you pass through the points. So like here, these were the points I plotted based on what I was given in this picture. And then make sure that the shape matches up. So I know I had to make this shape. I had to hit that point and it would stop making this shape where I drew my little guiding line here. So yep, to there. And then now I know on this interval, I'm making this shape. So up to here. And then I know I stop because there's a little guiding line. Here's another picture. Ooh, that's how it looks there. All right, we stop and we're making a new shape, this shape. And just making sure I hit all of those points that I've plotted on my graph. This does get long, right? Especially as we get into some of the nitty-gritties, right? But in general, the things that I'm going to ask you for on an exam, the things that I outline that are important when you're given a function and asked to draw its graph, are finding domain, intercepts, asymptotes. That's typically your first step. And the domain part is really just, most of the domain part is looking for asymptotes. Sometimes you run into things like square roots or logarithms, and those ones restrict the domain further. But a lot of times you're looking for asymptotes. So for intercepts, for the y-intercept, you're plugging in x equals 0. For the x-intercept, you plug in y equals 0, and then you're able to find your intercepts. Those are points that you're going to plot. Then the next bit of information you look for is for increasing, decreasing, and that's also going to give you your maxes and mins. So you do your increasing, decreasing by finding the first derivative, your critical values, or important values actually. Make yourself a sign chart, and then intervals of increase, decrease, maxes and mins. Find the actual coordinate point by plugging your value, your x value, back into the original equation. Next is concavity and inflection points. So you take another derivative and basically repeat the process, finding any inflection points. And then you put it all together. So I know it's a lot, but hopefully by reviewing this right now, you can then, when you're going through this review sheet on your own, kind of at least listen to me talk a quick recap about the subject you're working on at the time. So I'm hoping right now that just to give you enough information to aid you in your review. In particular, if you're working with rational functions and you're curve sketching with them, the vertical asymptotes are going to come from where the denominator is 0. The x-intercepts are going to come from when the numerator is 0. So with rational functions, setting y equal to 0 is the same thing as just setting the numerator equal to 0, and you solve for x. For horizontal asymptotes, you're looking at taking the limit as x goes to negative infinity or positive infinity. With polynomials, you don't have to worry about any asymptotes because polynomials don't have asymptotes, but rational functions will, other functions might. Well, rational functions won't always have, they won't always have a horizontal asymptote, but you have to check for them. All right. Curve sketching. So that was curve sketching. And you do not need to worry about slant asymptotes. We're not going to get into slant asymptotes. The last section, and I think the section that might be kind of divisive. Some people are going to love it. Some people are not going to love it. It's that second word problem section that we talk about. First was related rates. Next is optimization. So with optimization, oftentimes these problems are going to involve an optimizing equation, which is the thing you're trying to find the max or the min of, and a constraint equation that kind of gives you a bound. You're using, so if we look at like this very first example we did, where we had fencing, you're drawing a picture if you can, you're writing down relevant information. One of these is going to be an equation. So like one of these is going to be oftentimes like both variables are involved and it's equal to like a number. There's some kind of constraint here. And then that's your constraint equation. Your optimizing equation is going to be the equation of the thing you're trying to max or minimize. When it says enclosed area is a maximum, that means area is our optimizing function. The optimizing function is the function you ultimately end up taking the derivative of. You cannot take the derivative of the optimizing function until after you have substituted in the constraint information. Right? We have to substitute in the constraint information so that it's one variable. Now, if your optimizing equation is one variable from the get-go, which there are situations where that happens, then you don't have to worry about the constraint. But if your optimizing equation has two variables in it, you do have to worry about making that substitution so that you're able to only have one variable and then take the derivative. The really important part when you're doing these optimizing ones is that you're verifying that whatever value you're claiming is a max or a min actually is a max or a min. If the first derivative rather is nice, the second derivative test is oftentimes the easiest way to verify a max or a min. But if the derivative isn't nice, you may want to just do the first derivative test and make a sign chart. And then remember units in your answer. We did some problems, some other problems. One thing to mention that's a little bit different, we did this one business problem, and I mentioned to you that this problem was a little bit different. You're actually not doing the same checking process you did before. So if your problem has a constraint that's in a domain respect. So in this problem here that we did, if you remember back to the chairs one, we could produce at most 70 chairs. If you have restrictions on your domain, so you end up on a closed interval, instead you're treating it like a absolute extrema problem, where you're going to find your critical values within the interval and then plug in your critical value and both endpoints to see which of them gives you what you're looking for. In this case, we wanted to maximize revenue. So we plugged in 0, 70, and the one critical value in our interval, which was 50, to see which one gave us a maximum number. We're plugging them back into the original equation. And then we got to antiderivatives, which I'm not going to recap since we just finished talking about it, and that isn't going to be on the exam. So that's basically, those are the things that you need to be worried about studying. A lot of this, honestly, this section, these three are very interrelated. Optimization obviously isn't as related as these guys, but these guys together, you could honestly be studying them all at the same time. You could have one problem that somehow involves all three of those sections. So they're very, very interrelated. I really suggest doing the review before we go to the review on Friday. So there's a few problems. There's like 14 problems, and a few of them have a few parts. I tried to keep it as limited as possible so it wasn't an incredibly long review for you, but I do suggest trying all the problems out. The answers are included, but not the solutions. And then on the review session on Friday, which I think I'll do at 1 o'clock, I need to double check my schedule and make sure that I don't have anything going on Friday, but at 1 o'clock. I don't think I do. But I'll double check that and then I'll make an announcement about it. We'll go through the full solutions of the problems, but it'll be better for you in the long run to try these problems out on your own first before working them with me on Friday, because you're it allows you a chance to think about the problems and practice them before seeing how they're done. So I know that's a bit short for today. I'm happy to stick around and answer any questions that people might have. But I think that's what I'm going to do. I'm going to call it a bit early today to allow, I don't know, anybody who stayed up late last night to use that brain power to get through the rest of today. And if you have questions or comments or concerns and you want to stick around and ask them, I will stick around until everybody's gone. Otherwise, have a fantastic weekend. Work on that homework. The exam 2 regrades are the exam 2s are available for you to look at and then do any regrades you want to do. If you want to make up any of those problems, make sure that is submitted by next Wednesday. If you have questions about any of it, send me an email, and have a nice, safe, fun weekend.